Lower end theory and service. Lower end, rotating assembly of the cylinder block and all the internal components, crank, bearings, connecting rods, oil pump, and camshaft on overhead valve designs. Assembly is called the short block, and if that has cylinder heads, it's also called the long block. Here's a cutaway version of a V configuration engine. Here's a video.
The rotating assembly of an engine includes the crankshaft, the connecting rods, and the pistons. The easiest way to take apart the rotating assembly is with the engine upside down. As you rotate the block, there will be some coolant still trapped inside, so keep a catch tray handy and place it under the motor as you rotate the assembly. Next, look for a windage tray or screen. It's responsible for preventing oil from splashing onto the crankshaft. If your engine has one, remove it. Once that's finished, you can go ahead and remove the connecting rods and pistons. Start by removing the connecting rod's end caps and its bearing. Once removed, you can slide the piston and rod assembly down through the block. As you remove each one, be sure to mark it. The big end of the connecting rod should be marked in two places, above and below the parting line between the cap and body. This is important because the connecting rod caps need to be in the same orientation when they're reinstalled. The last step in removing the rotating assembly from the block is to remove the crankshaft. Loosen and remove all the bearing caps holding the crankshaft to the block. It's a good idea to mark these caps as you did the connecting rods. Next, lift out the crankshaft and remove the remaining bearings sitting in the block.
Short block assembly. We're showing the oil pan and water pump removed. You remove the harmonic balancer with a puller, be careful with that. Timing chain cover, oil pickup tube, and oil pump lifters, and keep all of the components in order so you know exactly where they go. Cylinder block assembly. A ridge may form at the top. Compression rings travel. The metal can be slowly worn away over time in this area right here, and that can form a ridge that will prevent you from removing the piston, because the piston rings have radial expansion and they're designed to seal, but if there's a ridge worn in the metal, that is the extreme version. There's typically a carbon ridge that forms first, but if there's a lot of miles on this block, you can't possibly have a ridge that's into the actual the bore itself. Okay, everything has to be marked. Now in the video, you saw the technician marking the connecting rods with a hammer and a punch. That will work on forged steel connecting rods. However, in automotive, there are some connecting rods that are made from powdered metal, which would shatter if you did that. So you'd have to use a paint marker or engrave or scratch your identification for the orientation of the bearing cap onto the connecting rod. Removing the pistons at bottom dead center for removal, the cap and the cover rod bolts to prevent cylinder damage. If you have a connecting rod that has studs on it, doesn't have bolts, you have to put covers over it. You'll see that in the next slide. These prevent scratching the bore. You also would have to be careful if you didn't have the threaded studs, because the sharp edges at the brake line for the big end of the connecting rod could very easily scratch the bore. Cylinder block assembly, you have to orient your bearing caps as they come off. They have to be numbered and know the correct orientation. Some engines they call it a bearing girdle or a bed plate. Now in the video you saw a bed plate coming off that particular engine, and that bed plate contains all of the lower main bearing caps. Have to remove them, and you want to take the rear main oil seal and bearing inserts off at that time, and pay special attention to the thrust bearing. We're showing the block core plugs. They're also called Welch plugs and freeze-out plugs, but however they have to be removed if you're doing a complete overhaul. Areas wherever you have combustion is going to be cast iron or ductile iron in the block materials, aluminum or magnesium alloys. Cast iron is very heavy, but it's strong. Ductile iron is actually heavier, but you need less of it, so you net out with a lighter assembly if there's ductile iron in the block. But aluminum is the block of choice in most automotive applications. We're showing aluminum block with a sleeve or a steel liner that's installed as a shrink fit process. Here we're showing the passages for oil and coolant in the block. Some engines even have passages for fuel. Reconditioning holes for cracks that are threaded. You should have a chamfer on it, and you want to clean them up with a thread chaser, a little bit of compressed air, and make sure that they are serviceable. A combination of helicoils where you have a correct drill size, a special tool to thread, and the inside of the helicoil is the thread that you started with and that you're working towards.
The internal threads on fasteners that are used to connect parts and accessories to an engine can become damaged over time. In many cases, threaded inserts will allow you to repair the damage so that the hole can be used again. The first step is referring to a drill chart to determine the correct type and size of tap for the job. Next, drill out the damaged threads from the hole. Then, using a thread pitch gauge, confirm the readings from the drill chart and select the corresponding size and type of tap, which will be either a taper, intermediate, or bottoming tap. Once you've made your selection, take the T-handle wrench that was included with your kit and attach it to the tap. Then put on a pair of protective gloves and coat the hole to be tapped with cutting fluid. Once you've applied the cutting fluid, align the tap so that it's square with the damaged hole and slowly turn the tap wrench clockwise. As you turn the tap and feel the new thread being cut, it's always a good idea to reverse the tap several turns, just to make sure that you keep the cutting threads clean. Continue to turn the tap until you hit bottom or pass all the way through. To remove the tap from the threaded insert, turn the wrench counterclockwise. There's bound to be metal filings on the tap, so make sure to thoroughly clean the cutting thread before putting it back in the kit. To finish the job, clean out the repaired hole, and then test it by placing an insert on the tap installer and thread it into the tapped hole.
There's some good points there with the flat bottoming tap. If you're doing a blind hole, you probably want to get your threads down below. If you're doing helicoils, the kits typically come with the correct tap. That's a special tap size for the helicoil, and they give you the drill bit size, and some kits will give you the drill bit itself. But you do have to refer to the machinist chart to make sure that you do have the correct drill bit. You have to be careful if you're working in aluminum, because aluminum's a softer metal, and the helicoil is typically 316L stainless, and it's a lot stronger than the aluminum, so you have to get it right. It takes some finesse and practice to learn how to do helicoils correctly, but they are a lifesaver in terms of keeping an assembly in service. Here we got block reconditioning, and we got flatness check. The number here, maximum amount of unstraightness or unflatness is 4 thousandths. That's the number that is a generic specification. And we have the straight edge is a certified machinist straight edge. It has to be certified perfectly flat, otherwise it's not going to be useful in determining the condition of the deck, and also on cylinder heads you do the same thing. Typically the wear is going to occur at the top of the cylinder where you have all the heat and all the pressure occurring during combustion, and that's where the most potential for wear is. So you're going to have that situation of taper, and you only have an allowable amount of specified. You look that up, but it's typically around 1.5 thousandths. In some cases, it could be more, depending upon what's called out by the manufacturer. The crosshatch. The crosshatch is very important because it'll hold enough oil so that the rings can be lubricated in their travel from bottom dead center to top dead center and back down. If the rings are not seated correctly with crosshatch and oil, they're not going to break in. It's considered what's called the 60-degree crosshatch, and it does have a micro-inch finish specification called out by the manufacturer of either the piston and the rings or called out by the OE. So you have to be careful that you understand that the surface finish has to be in conjunction with the type of rings and the type of surfaces that the bore has. So that is something that you need to know before you start putting surface finish on your bore. Deglazing will take off the coating that happens just from normal combustion. Boring, when the walls of the cylinder have damage deeper than 1 or 2 thousandths, the block most likely has to be bored out in automotive at 10 and 20, 30 thousandths, depending upon the amount of material in the block. In some cases, there's 30 and 40 thousandths over, but oversized kits are available with a combination of pistons and rings for that purpose. What may result if the cylinder bore finish is too smooth? Okay, you're going to write that down and email it to me, right? Lifter bores. Lifter bores can create problems, multiple problems in the block and also in valve train. So we want to make sure that the bore is correct and that it has the right amount of circumference and concentricity, and it's not out of round. Otherwise, if it exceeds that wear limit, the block needs to be replaced. Crankshaft, main bearing saddle alignment. The bearings in the main have to be perfectly straight and concentric and to each other. This is typically done with a special tools. They're showing the technician here using a flat bar that will only give you a specific amount of flatness and orientation on your main bearing bores. But this is usually done in a specialty shop that has laser measurement equipment, and they can do a line boring, they call it, but it's honing because it's removing a very small amount of material just to set the specifications for all the main bearing bores. Installing core plugs. Core plugs typically go in with a non-hardening sealer. That is your test question answer. That's going to be on the ASEs forever, but it's important to note. Okay, cam bearings. Cam bearings are one piece and they're pressed into the cam bore. In overhead cams, they can be split bearings, but in some cases you're going to find aluminum cylinder heads, overhead cam cylinder heads that have no bearing. It's just oil running through a gallery onto the hardened polished steel journals of the cam. So you may see situations where there are no bearings in the overheads on a lot of gasoline engines. Balance shafts. Balance shafts are there to reduce the energy of the crankshaft turning, and there's always a bit of energy that moves out into the block. There's torsional forces as the crankshaft spins, and the counterweights that are in the balance shaft reduce the amount of harmonics that flow through the block. So it's very important that if there's a balance shaft that is perfectly timed to the crankshaft. And there's a variety of ways to do it with gears and with chains. With chains, they may have a black link that goes to a timing mark that's on the crank and the balance shaft. A balance shaft, again, very straightforward. You're going to see these in engines that are out there today. And balance shaft, you have to be very careful and understand that there are specifications to install them correctly. Cranks are made from essentially forged steel. They have machining work to have journals that are polished to a mirror finish, extremely close tolerances. You have an oil film between the journal and the bearing, which is fed in through oil galleries in the block. That is called hydrodynamic suspension. Crankshafts and camshafts are floating on oil. If they're not floating on oil, you have a concern for quick destruction of the rotating assembly. Here's a basic crankshaft here. We're showing main bearing journals, a rear where your flywheel or flex plate bolts up, and the front piece where your harmonic balancer would generally be, and your connecting rod and main journals.
Crankshafts are typically cast or forged into a single piece using heat-treated alloy steel, which gives them a great deal of mechanical strength. The crankshaft is connected to the piston rods and the flywheel, and uses crank throws to convert the linear motion of the piston to a rotary motion. Throws are offset from the axis of the crankshaft and connect the connecting rod from the piston to the crankshaft. An engine needs to be balanced in order to operate smoothly. Throws are balanced during construction with counterweights. If fine balancing is needed, the throw can be drilled out, or smaller weight could be added. The crankshaft rotates in bearings. Bearings are lubricated under pressure with oil that travels along a groove in the bearing. Bearings are also located on the crankshaft, where the big end of the connecting rod connects the piston to the crankshaft. The rear of the crankshaft is also drilled and tapped for flywheel attachment. Near the front of the crankshaft, a timing sprocket is responsible for driving the camshafts. The piston's power stroke slightly twists the crankshaft, which could result in torsional vibration. Torsional dampers are placed at the front nose of the crankshaft to reduce vibration.
Torsional dampers. Dampers are important to balance out what's called harmonics. Anything that moves creates sound waves. If the sound waves are significant enough, they can't cause damage to metal. So the harmonic balancers have to be perfectly balanced. If you see any wobble or any distortion in a harmonic balancer, it should be replaced. And the destruction of the crankshaft and the rotating assembly is possible if you do have balancing concerns with the harmonic balancer. Called the vibration damper. There's hubs. Some have rubber inside. Some have liquid silicone. Pretty straightforward. There's generally no real servicing of these. Can't remember any core value for them. Possibly is. Okay, fluid dampers have the high viscosity fluid. I believe that's silicone. A flywheel or flex plate. Flywheel, flex plate will keep the force of the engine moving. With automatic transmission is the flex plate, and the torque converter will act as the flywheel. Crankshaft inspection is essentially in the shop. You're going to be doing a visual inspection for overheating. The signs of heat effect would be bluing of the metal, or worse, brown or black, and scratching, scoring, wearing, scuffing of the journals. Also, you can do a thorough and a well-lighted bench looking for cracks. You'd also want to use your magnetic particle on that for crack detection. Here we're using the micrometer to check out of round and taper. Any minimal amount of out of round and taper will greatly affect the film of oil that hydrodynamically suspends the crankshaft while it's turning. So here it's very important that you're able to read a mic well, and you're able to understand why you need these very close tolerances on your polished journals. Crankshaft reconditioning. Typically, crankshafts can be cleaned, magnafluxed for cracks, balanced, and they can also be ground. If there's a situation where there's some damage, they can be ground 10 or 20 thousandths for most automotive applications and more for larger engines. They're going to come with a rebuild kit that's going to have a larger bearing that corresponds to the amount of material removal. Crankshaft straightness, you need a good set of V-blocks, and indicated that a good crankshaft shop can do this recondition of the crankshaft and check everything. It's money well spent if it's a high-valued engine. Bearings are typically a combination of materials. We're going to get into that in a moment, but typically we're going to have an individual bearing cap, and we're going to have a combined bearing cap assembly instead of individual bearing cap called the bed plate. And this is on automotive applications. They have shown up in a few diesel applications also. But there are very specific tightening procedures and detorquing and torquing procedures for bed plates, because you have multiple tensions being applied, clamping forces being applied to the bed plate, and it's got to be perfect because you have a lot of load from the crankshaft going into the bed plate. Here we're showing the thrust bearing. The thrust bearing has sides on it, and those sides create limit the amount of travel or crankshaft end play. There's a specification which will be a range. You'd like to go to the lower side of the range if it's a complete overhaul. You want to make sure that you have your specification determined by your manufacturer's specification literature, and make sure that you do a combination of tests and make sure that your end play is perfect. Your bearing is typically harder material on the bore side and softer material on the inside. That has changed in some applications where they're putting very polished surfaces on the crankshaft journals, and they're using more durable material on the inside, what they call the babbitt. Okay, we have several concepts here. The bearing spread is slightly greater than the bearing housing bore. And when the bearing is installed, it has a small amount of material that protrudes past the housing, and that is clamped to the block portion that has the other half of the bearing, and when that's torqued down, you have what's called bearing crush. So you have bearing spread and bearing crush that keeps the bearing together, and also to keep the bearing in location. This is also called a tang, or a locating slot. It's only on one side of the bearing, and that's going to give you the correct orientation. You want to make sure that you never oil the housing bore. That bearing has to go in dry on this side. Your only concern is that the bearing, the journal surface has the oil, but you don't want to put oil on the housing bore. The flange main bearing is the controls end play. It's a thrust bearing. Installing main bearings and crankshaft. There's little to no wear on journals. You might be able to get by with standard size main bearings. If there's any type of wear, the crank has to be ground among other services in a specialty shop. They'll grind a crank, they'll balance it, they'll clean it, they'll do magnifluction and inspect for cracks. But undersized bearings are oversized. It's the journal that has the material removed, and it's the bearings that are supplied that are oversized. You have to be very careful because there are situations where the wrong bearings get mixed into a ground bearing replacement kit. So you want to make sure that you're able to mic your bearings and, of course, use plastic gauge to finish each application, and that will give you assurance that you have the correct amount of clearance between the main bearing and the hard polished journal of the crankshaft.
Begin by installing the crankshaft bearings. Once the bearings are in position, take a main cap and place it over the studs or bolts that are part of the crankshaft assembly. Apply some fastener solution and torque the main cap to specification. Next, take a micrometer and measure the outside diameter of the crankshaft. Then, using those measurements, set up a dial bore gauge and compare the measurement between the crankshaft and the bearings. The difference will be used in determining the clearance for the crankshaft during final installation. After determining the clearance for the bearing, repeat the process for each bearing, and then remove all the caps. With all the bearing caps removed, the next step is applying lubricant to each bearing and then carefully placing the crankshaft in the block. Once in the block, apply additional lubricant to the crank throws. Next, reinstall and hand tighten each cap. Then, using a mallet, tap on the end of the shaft to line up the bearings. One of the last tasks is checking end play. This is done by mounting a dial indicator to the rear of the cylinder block and prying the crankshaft with a flathead screwdriver. Next, set the dial to 0 and pry the crankshaft in the opposite direction, and note the reading to make sure it's within specifications. Once the crankshaft has been completely installed, it should rotate freely.
You notice that the technician had approximately 7 to 8 thousandths of end play, which sounds okay for that engine. I've seen this technician in several videos with different engines, a Merlin 502 GM style. He was building in another video, and you got to pay attention to what's going on in your crank. Here we're showing a bearing that has been designed for a 30 thousandths of a ground crankshaft. So they grind the crankshaft 30 thousandths, and the bearing is 30 thousandths thicker to accommodate for the material removal from the journal on the crank. It's pretty straightforward, and once you see it, but you want to be careful and make sure that you have the correct bearings in your oversized kit, and they call it undersized crank, oversized bearing. That's one way to look at it. Installing bearings and crank continue. We use plastic gauge both on the main bearings and on the connecting rod to make sure that we have the correct clearance for oil between those polished hardened journals and the connecting rod small and big end and the main bearing end. So you're cleaning all the oil off, you're removing the cap, you're putting the thin thread of either green or red plastic gauge on green for automotive, most automotive applications, and green or red for diesel. You're going to have the envelope to be very careful because that little thread could drop on the floor. You lay it on the longitudinal portion here, and you install and torque down. We typically will put down about 2/3 to 3/4 of the final torque on that. That's enough to get the crush of the plastic gauge and get the reading that you match up to the graphic that's on the package, and it will give you the clearance here. He's showing a 2 thousandths clearance, and if that's within the called out clearance that the manufacturer recommends, you're going to move forward. Crankshaft end play, we saw that in the video. There's a few ways to do it, but feeler gauge and dial indicator is used. On very large engines, we use feeler gauges. On smaller engines, you could use a dial indicator, but a combination of both or either or is adequate, as long as your end play is adequate for the range, hopefully on the lower side of the range that the manufacturer is calling out. If it's more than the range, you have to replace that main thrust bearings and washers, and if you're replacing one main bearing, you probably should replace all of them. Okay, and they're showing that the rear main seal is installed during the final installation of the crank. Here a little graphic showing us utilizing feeler gauges for end play, and here we're using a dial indicator and a magnetic base on the nose of the crankshaft. Connecting rods can be a variety of materials and geometry based on the service. Some have drilled holes in them to deliver oil up to the pin, the small end. Typical application here. Now, crankshaft throw, the offset of the crankshaft main bearing center to the offset of the crankshaft connecting rod center is called the crankshaft throw. The stroke of the engine is twice the crankshaft throw. That's the magic number there. It's twice that dimension. So from the center line of the main to the center line of the main bearing to the center line of the connecting rod bearing is half of the stroke. So you double that dimension and you have the stroke of the engine.
The connecting rod connects the piston to the crankshaft. It's fastened to the piston at its little end by a piston pin. In some engines, the pin is pressed into the small end of the connecting rod, while other engines use a floating pin design, which allows the piston and the connecting rod to rotate on the pin. The pin is held with circlips, which requires a bearing in the small end of the connecting rod. The big end of the connecting rod is split in order to fit onto the one-piece crankshaft. The detachable portion is called the big end cap, which is clamped to the connecting rod with nuts and bolts. Connecting rods need to be lightweight, but at the same time strong enough to withstand a great deal of mechanical stress without twisting or bending. These rods are drop forged from steel alloy, and in order to withstand mechanical stress, high-performance connecting rods are typically constructed in either an H-beam or I-beam style. And because engine balance is such an important factor in overall engine performance, connecting rods in the engine are always manufactured and packaged in matched sets.
Getting over back to the connecting rods, they're typically going to be forged steel. You're going to see some connecting rods that'll have a variety of alloys and materials, and also remember that there are powdered metal connecting rods out there that have strength. They're a bit lighter and they're cheaper to make because it's a casting of powdered metal in a casting, and it will hold up in automotive applications. So those are also out there. Moving on to pistons and piston rings, you're typically looking at aluminum alloys. Pistons can be flat, concave, convex crown, and also have reliefs cast and machined in for valves. So there's potentially less interference. Typically that's done, you see that on the intake valves because they have more lift. Okay, here we're showing two compression rings and an oil control ring, a pin, connecting rod, and the big end showing the cap and the two bearing halves. Okay, they're calling this two types of skirt. There's slipper skirts, full skirts, and some pistons without skirts. Okay, this is a unique geometry here we're looking at. Taking a look at the top of the piston has a direction mark that's in it, pointing towards the front of the engine. Okay, any types of cracks, scuffing, on a minor amount of scuffing is standard on a piston. The skirt is rocking a bit before it heats up, and it's cam ground, so it's got to warm up a little bit to become fully round. So a small amount of scuffing on the skirt is permissible. Ring expanders, to remove the rings, you got to be careful because you're taking a hardened steel ring and that has a radial expansion, but once you open it up, it can become a projectile. So you want to make sure that you have shop glasses on, and it's possible to lose the ring out of the tool. So you want to be careful with that. You have to clean all the carbon off the top of the piston and the ring grooves. You have ring groove side clearance. There has to be a specific amount of play between the ring, the thickness of the ring, and the thickness of the opening for the piston ring groove on the piston. If the ring doesn't have that specified amount of movement, the ring's not going to last, and the engine isn't going to last. So that's going to be important to pay attention to. Pins. There's hollow steel tubes in most automotive applications. They have to be perfectly round. You have a variety of how the pins are put together. Semi-floating, the pins are pressed into the rod. Sometimes that's hard to press them, and they are frozen in the freezer while the rods are heated in an oven to 400 degrees, and you can insert the pins on the semi-floaters that way, or you can send them out to a shop that'll inspect all your rods and install your pins and pistons, depending upon the capability of the shop. Full floaters are the easiest because everything comes apart. Okay, here's an example of, they're showing the full floating here, the way it looks, so that the pin is going to have motion once you remove the lock rings. There's pins. Anything that causes the piston to wobble failure is on its way. So the pin bore and the pin has to be perfect. Otherwise, you're going to have to send them out for a service. Connecting rods may have a pin bushing, which is a wear sleeve. That's a bronze material that's pressed into the small end, which is the pin end. Okay, combustion chamber. That top ring lives in hell. There's a lot of heat, there's potentially carbon, and you have less oil at the top, so at the top ring as it comes into the heat of the combustion area. So you want to make sure that the rings are installed correctly, and make sure that the specifications are followed exactly as called out by the manufacturer. Different types of rings, compression rings and oil control rings. These have evolved over the years. Engines in gasoline and diesel have had a variety of ring configurations, but today we're typically 2 compression rings and 1 oil control ring is pretty common. This is what's shown here. We have some other concerns with rings. Piston ring end gap. You have to install a ring only into the cylinder, and you have to use a long feeler gauge at top, middle, and bottom dead center, and you have to have a certain amount of gap with that piston in the block, in that bore, to be within specification. And piston rings will have a correct side facing up, so you're going to see a dot or an orientation mark that's in there. And the ring gaps have to be within specification, or the engine's not going to last. They're showing it this way. Let's just say we're looking for 12 thousandths, 10 to 12 thousandths, 8 to 10 thousandths here. You have to be within the range that's called out. You're going to push the ring down from top to middle. Take it again. You may need a longer feeler gauge to get to bottom dead center, and you're going to check the ring there. If you have a differential between, if you have more piston ring end gap at the top position than middle and bottom, you have taper. So that is another way that you can actually find taper, is doing end gap. This is piston ring offset or stagger for the ring openings. The A, they're showing the oil ring spacer opening on the oil ring. B, oil ring rail gaps. And C is the second compression ring gap, and D is the top gap. So they want stagger amongst the gaps in the oil and compression rings.
Once you've measured the pistons and bored the cylinder, you can go ahead and install the piston rings. Piston rings are available as standard out of the box or file to fit, and because the fit is crucial, all piston rings need to be fit checked for side clearance and end gap. To check the fit, insert a ring into the cylinder bore. Then, using a squaring tool, push the ring down into the bore. Next, use a feeler gauge to measure the gaps between the ends of the ring. If the gap is smaller than the required specifications, the 2 ends can be filed to the correct size. Once you finish filing, remove any burrs that may exist at the ring tips. Once you've determined that the ring is ready for installation, assemble the piston and connecting rod and rest it on the edge of the cylinder head. Next, install the piston rings in the following order. Oil ring first, followed by the second ring, and finally the compression ring. After the rings are in place, lube the cylinder and compressor. Then position the crankshaft to accept the piston. Once that's finished, position the piston and drive it down the bore with a piston installation hammer. To finish the job, turn the engine over, attach the cap to the connecting rods, and torque to specifications.
It's important to note that he was putting the oil control ring on first, and he puts the expandable piece on, and then he puts the lower portion of the oil control ring on, then the upper portion, and that has to be the openings of both the three pieces have to be staggered in accordance to that diagram, and that could change based on manufacturer. So it's going to be oil control ring, second compression ring, and then the first or the top compression ring. That would be the order in that application. Your caps and your rods are matched, and that everything was marked so you know your orientation. You have to oil your cylinder walls, and you have to put oil on your journals as well. And after each piston is installed, you have to rotate the crank and make sure you got smooth rotation without any binding. If there's any binding whatsoever that's noticeable, you got to take it apart and find out what the problem is, because you can't put the engine together that way. We would rather delay the job than give the customer something that's not going to last a long time. Okay, checking for crankshaft rotation after installing each piston. It's pretty straightforward. However, it needs to be done. Camshaft and related parts, all of the journals on the cam need to be inspected for any type of scoring, scuffing, splitting, cracks, or any type of abnormal wear. The greatest cause of failure is lack of inadequate lubrication, not having clean oil in the overheads. A lot of vehicles that have overhead concerns aren't serviced correctly, so they are getting dirty oil and a lot of abrasion up in the valve train, and that is a problem. So you're going to see that if the engine comes out of a vehicle that has that service history. We have journals that need to be measured, and straightness with a dial indicator. You need a good set of V-blocks to do that. Okay, timing components. You have essentially you're going to have a gear on the crank, and you're going to have a gear. This could be a double overhead cam engine. It's going to have 4 valves per cylinder most likely, and you need to have all of these components have to be within specification for lash. So we're going to be going over that in shop. Okay, lifters. You have a variety of lifters, but it's again improper lubrication is a concern. Everything has to be cleaned. You have oil gallery holes in lifters today, and they have to be perfectly clean and blown out. You never use old lifters in a new cam or vice versa. If you're replacing the cam, you're replacing the lifters. Convex, flat, and concave. So convex is obviously acceptable. Cam bearings, that's pretty straightforward. They have to be press fit in to the block with a tool on a rod. And there's different diameters in some engines, so you want to be careful that the smaller is at the rear and that the larger would be forward towards the front, and make sure you understand what the progression is for removal and what the progression is for install, because there are concerns when you have different size bearings. Camshaft tool. This is a centering cone, and this is the actual tool that's going to either remove or install the bearing. Okay, obviously you're going to coat them with assembly lube because you're not going to have any oil pressure for a moment, and you don't want to have any dry start, so there's got to be some appropriate assembly lube in all those locations. You have to lubricate the lifters and install the cam to avoid any Bearing damage, very carefully. You don't want to be bumping the hardened journals against bearings. You have a thrust plate and a cam gear, and once again, you're going to turn the cam by hand and make sure that there's no binding and very smooth. You're looking for a very smooth rotation. Cam and crank and cam timing. Timing marks are there. You need to know where they are, why they're important, and make sure that you have the correct devices to hold, let's say, cams if necessary. There are some special tools. You can also utilize some other clamping tools as long as you're not doing any damage to the part and you're arriving at good timing mark alignment. Here we're showing very straightforward here with the two dots. Obviously, the crank versus the balance shaft. The balance shaft is going to have either a chain. Sometimes the chain has a darkened spot on it. I know some of the Chrysler small engines had it that way. Some of the balance shafts are going to have gears, and you're going to have timing marks on there. But it's very important that you understand the orientation of the timing for balance shafts. Otherwise, if it's that's not done correctly, it'll go together, but it probably won't last. Okay, so you have bearings and journals. You have to check the oil clearances with plastic gauge, and you want to align the timing marks and set the shafts in position. Oil pumps, positive displacement pumps. This is a amount of oil that's entered is equal to the amount that leaves, but it's proportional to the pump speed, and your oil pressure is going to rise based on RPM. But it's also affected by oil viscosity, temperature, and the frequency of service. Engines that have the correct frequency of oil changes have less probability of sludge and wear, so those engines will most likely have better, cleaner oil galleries and better oil pressure over the life of the engine. Engines that don't have the correct oil service intervals is going to develop sludge and dirt throughout the engine, and those would have to be won't last as long and would be candidates for early rebuild or replacement. Balance shaft not properly timed, bada bing, bada boom. That's the correct answer on your test. Types of oil pumps, we're showing a gear style pump. They generally last the life of the engine. This is a gear rotor or a rotor gear rotor. It's Parker Hannifin invention. Years ago, they were using many large types of industrial pumps, but in oil pumps, they work really well because as it spins, it compresses the oil and it makes pressure. Today, they also have constant velocity pumps that are used in applications where you have the same oil pressure regardless of RPM. So there's a lot going on there. But in the real world, if you're concerned that your oil pump has a lot of time on it and it has a little bit of slop that he's measuring for, you're probably going to want to install a new oil pump. It's low cost, and you're probably not going to be able to get to it once the engine's put together. Not all the pumps are accessible from the bottom of the oil pan. So it would be good practice to replace the pump if you're not sure, if it's got a lot of miles and it has clearances that are borderline. Thank you.